Is 225 divisible by 3? 225 is divisible by 3. Now, what about the square of 225? Is this number also divisible by 3? Well, the answer is yes. If a number is divisible by a prime number, then so is its square. What about its converse? Well, the converse is also true. There actually is a theorem which states that if a is a non-zero integer and p is a prime number such that p divides the square of a, then p divides a also. Let us see some extensions of this theorem. Let's fill the table shown here. As we can see, the values of a, b, and p are given. The product of 12 and 9 is 108. 108 divided by 3 is 36. 12 divided by 3 is 4. And 9 divided by 3 is 3. Let us now look at the next set of values. The next values for a, b, and p are 18, 15, and 5 respectively. The product of 18 and 15 is 270. 270 divided by 5 is 54. 18 is not divisible by 5, so we put a cross, and 15 divided by 5 is 3. The next values for a, b, and p are 28, 3, and 7 respectively. The product of 28 and 3 is 84. 84 divided by 7 is 12. 28 divided by 7 is 4. And 3 is not divisible by 7, so we put a cross. What do you observe about the values of p? We can see that p is always a prime number. Can we say that the product of a and b is always divisible by p? Yes, we can see that in each of the examples, AB is divisible by p. Are a and b always divisible by p for every example? No, we can clearly see from the table that a and b are not always divisible by p. Thus, from these observations we can infer that for any two non-zero integers a and b, p is a prime number. Then whenever p divides ab, then p divides either a or b or both a and b. This result is a theorem on irrational numbers. Let us see another theorem on irrational numbers. Look at the values given for the variables a, n, and p and fill in the missing values. 4 raised to 3 gives 64. 64 divided by 2 gives 32, and 4 divided by 2 gives the answer 2. Let us look at the next set of values. 14 raised to 2 is 196. 196 divided by 7 gives 28, and 14 divided by 7 gives 2. 30 raised to 4 is 8,10,000. 8,10,000 is not divisible by 11, so we put a cross. The number 30 is not divisible by 11 either, so again we put a cross. What do you observe about the values of p? We can see that p is always a prime number in each of the examples. We know that a prime number is divisible only by 1 and itself. Observe the answers that we have written for the last two columns of this table. What is your inference? We can clearly see that if a raised to n is divisible by p, then a is divisible by p. And if a raised to n is not divisible by p, then a is not divisible by p. Thus we state the theorem as, if a is a non-zero integer, n is a positive integer, that is a number more than 0, and p is a prime number, then if p divides an, then p divides a. Recall the result we did in the beginning. If a is a non-zero integer and p is a prime number such that p divides the square of a, then p divides a also. Let us compare it with theorems done now. This theorem is a special case of first theorem where instead of 2, we have one number a. In the second case, the power 2 is extended to any number n. Can you find a rational number between the two given rational numbers? For any two rational numbers, half of their sum is always a rational number that lies between them. So, to find the rational number between the given rational numbers, we find the half of their sum. On simplifying, we get 39 by 55. Thus, 39 by 55 is a rational number between the two given rational numbers. Is there any other rational number between 3 by 5 and 39 by 55? To find a rational number between two given rational numbers, we find the half of their sum. On simplifying, we get, thus 36 by 55 is a rational number between the two given rational numbers. Would there be any rational numbers between 3 by 5 and 4 by 5? To find a rational number between two given rational numbers, we find the half of their sum. On simplifying, we get, thus 7 by 10 is a rational number between the two given rational numbers. Thus we can see that between the rational numbers 3 by 5 and 9 by 11, there are many rational numbers. We even found a rational number 7 by 10 between the rational numbers 3 by 5 and 4 by 5. Thus we can infer that there are infinitely many rational numbers between any two rational numbers. Do you think any irrational number exists between the numbers 5 and 6? Let us find out. Let us consider the squares of the given numbers. The square of 5 is 25 and the square of 6 is 36. We know that the square root of a non-perfect square is an irrational number. Thus, the square root of any number lying between 25 and 36 is an irrational number. Thus, some irrational numbers lying between the numbers 5 and 6 are the square root of 26, square root of 30, and the square root of 32. Will there be any irrational number between the square root of 26 and the square root of 27? Let us consider the squares of the given numbers. The squares will be 26 and 27 respectively. Thus, the square root of any number lying between 26 and 27 is an irrational number. Some numbers that lie between 26 and 27 are 26.5, 26.02, and 26.9. Some irrational numbers lying between the square root of 26 and the square root of 27. Thus, some irrational numbers lying between the numbers 5 and 6 are the square root of 26.5, square root of 26.02, and the square root of 26.9. Thus, we can infer that there are infinitely many irrational numbers between two different irrational numbers, like between the square root of 26 and the square root of 27. And we can also infer that there are infinitely many irrational numbers between two different rational numbers, like between the numbers 5 and 6.